Hello, everyone, and welcome to week 3 of our summer class. Today, we're going to be talking about generalizability. So, after spending a lot of time already on internal validity, we're going to move into external validity. Today, I have ready for you some material about generalization, and then we're going to get into p-values and uh, why we use them and maybe some better statistical approaches that we can use to tell us about how large effects are. Um, there is some uh, content in this class that is not for children. I'll give you a heads up um, about this. It's a disgusting example that's used, and it's an experimental manipulation. Um, so let's go ahead and jump into it. So first, generalization is one important goal that we have in science. Uh, Generalization is when we use sample statistics to make inferences about the population. We don't have access to the entire population, but you might have noticed as you were watching the election results for our most recent presidential election, not this one in 2012, but the 2024 election, that they were able to call states way before those states' total number of votes were in, sometimes even as low as 10% of the votes in. Um, and how are they able to do that? They're using sample statistics or a subset of that state's population, their voting data, and uh, based on that, they're able to make inferences about the population. Okay, so this is what we're doing when we generalize. We can generalize to people. Um, One way that we can do that is through representative sampling. Um, and this is when the demographics match those of the population. So, for example, if we wanted to generalize to all Radford students in a psychology study, we might make sure that the students we sample match just about the demographics of students at Radford. Another way that we can approach that is through random sampling, in which everybody in a population has a random chance of being involved in the study. This is different from random assignment, which we've discussed previously. Random sampling is whether you're involved in the study or not. Random assignment is which group in the independent variable you're assigned to. If you're not doing either of these things, then it's really difficult to generalize to people outside of the sample that you're studying. You can also generalize to contexts. So, for example, your field studies in this class um, will be very generalizable, considering that you're going to be studying people out in the real world. Because field studies happen out in their natural environment, we can assume that those results generalize to that context. Um, Lab studies are a little bit harder to generalize to real world contexts unless they're higher on mundane realism, or in other words, kind of like the crutches study that I did, where participants had the opportunity to give up their seat to a person on crutches, and this person was an actor involved in the study. So we're able to generalize to social context in a study like that, even though it's occurring in a lab, because the situation we created is really similar to something that might actually occur out in the real world. So this is, who and what we can generalize to. But one thing to keep in mind is that science has a problem. We are weird, and weird is an acronym that stands for the participants who we typically study. Who usually makes up folks in psychological, who usually makes up the samples of folks in studies in psychological science, and it's people who are Western educated, industrialized, rich and democratic. This is where folks typically come from. Democratic here, not referring to the political party, but to a guiding principle of how a nation makes decisions. So we're not weird in this way. We are weird in this way. This is the cast of Beverly Hills 90210. If you don't know what that is, ask your your parents or guardian, uh, they'll probably know. Maybe we're getting to a point where you might actually have to ask your grandparents about this, but I don't think that we're quite there yet. So if this is what folks look like in our study, how can we generalize outside of this particular population? And the short answer to that is we can't. Here's some examples of why we're not able to generalize basic findings in psychology. So take a look at these two lines and just in your mind, answer the question, which one is shorter? Now, one common finding in research is that even though these lines are exactly the same length, many people will say that this line appears shorter than this one. It's a perceptual illusion that you're seeing here. But depending on where you're from, you might not see a difference between these lines at all. Uh, on this graph, you can see on the y-axis, it's how different the lines are perceived to be. And then on the x-axis, you see different cultures. So here we've got Evanston, which is, I think, in Illinois, very Western culture. And they're seeing these lines as very different, or in other words, they're seeing this one as much shorter than the other. But depending on the culture that you're in, you might see very little to no difference at all between these lines. And this is important to know because we can't just take research like this and assume that it generalizes to everybody. We can't assume that it's a universal property of human cognition. Um, so something to be mindful of when we're doing weird science. Another example that I'm going to show you, and this is the one that's a little disgusting. It's very disgusting. Uh, and if it's not something that you want to watch, that's fine. But it's a brief story or a vignette. So this vignette was not created by me. It was created by Jonathan Haidt. So I'll just let you go ahead and read this as it's coming up on the screen. Okay, disgusting, right? Okay, we'll put an end to this very soon. I'm sorry that you're having to look at this. But Jonathan Haidt has designed studies to test this idea that our morality is driven by an emotion called disgust. And what he thinks is that people will do their best to try to rationalize why this this story that you just read is disgusting. Um, and and instead, they're really just making this decision that no, what you just looked at is not okay. And the reason is not something that we have actual access to. So one thing they find is that college students will do their best to try to rationalize this disgusting example. Or in other words, they'll make up reasons for um, why it's disgusting. When in reality, the real reason is it just makes us feel icky. Um, so even though these college students are not more rational than anybody else, they'll spend more time rationalizing, trying to give some logical reason as to why this is disgusting. Whereas if you go to folks over in the Charlottesville McDonald's, this is a professor who was at UVA at the time he was doing this study. They would say something along the lines of, "What in the world is wrong with you? This is just gross. I don't need to give you a reason why it's gross. It just is." Um, so one of the findings here is that um, this process where people will try to be rational even though they aren't doesn't actually generalize even into folks in the same city as the college students. So one of the downsides of collecting weird samples. Some other things to think about if we're just studying college students, and this does make up a big subset of our psychological literature, is that college students are more compliant. If you've uh, taken a social psychology class, you may have heard about the 1959 study from Fessinger and Carl Smith, in which participants were asked to turn pegs for several dozens of minutes. Just a really boring task where they're quite literally turning wooden pegs. And then they were asked to lie to the next participant about how fun that this task was. And this is not something that most people will sit through, but college students were willing to sit through several dozens of minutes of this task. College students are also more readily able to change their attitudes. There's been some research in which uh, students are asked to either elaborate on an argument that's being made in front of them or not. And college students are usually pretty, ready to change their attitudes. Uh, they're less resistant to attitude change than the general population. And students don't usually base their perceptions on introspection. Um, or in other words, students will think that they're introspecting, but they're really not. One example of this comes from research in which students were asked to give reasons for why they chose a certain uh, thing to purchase, and they were able to give lots of really elaborate reasons, but really had to deal with where the item was sitting. So this was that study in which they used nightgowns as the item. And students tend to think they're more rational, but they're really not. So from this, we just saw an example from Jonathan Haidt's research in which they took a disgusting thing and tried to give a reason as to why it was bad or gross. And most people, or in other words, non-college students, will tell you hey, this is really gross, and I don't need to tell you why. So they're not more rational, but they tend to emphasize it more. So one direction our research has been going is in terms of studying real behavior, which folks are looking at as more generalizable. Um, and over time, our research in social psychology has become more and more pen and paper based. And this is because of our social cognition movement that came around in the 1970s, both for ethical reasons and also because we were able to use computers as a model to study the human mind. Um, we began to move more toward asking people to think about how they might act in various situations instead of just putting them in those situations. But we are starting to get back to our roots of studying real behavior in stage scenarios, whether that be in the lab or naturally occurring environments out there in the real world. So for a while, our research has not necessarily been generalizable, but it's moving in that direction. So another thing that we want to think about, considering that statistics allow us to generalize to the population, is what in the world does this p-value of less than or greater than 0.05 tell us? We're probably thinking about this back in terms of our Psych 301 days, and that's exactly where I want you to go. So why do we use p-values to tell us whether something is meaningful or not? And where did it come from? In science, it's our criterion for significance testing. Right? It's a probability. If our data are are true, or sorry, if our data um, that we got are based on this idea that nothing is really going on in reality, maybe in a land where we have unicorns and rainbows, um, and the rainbows end at Arby's. In this world, we always believe that the null hypothesis is true. And with that belief, when we collect data on a study, it tells us the probability of us getting that data or that result again, should we redo the study. And so we aim for studies to have really low probabilities of their data. So we can say, yes, these means are different. Or in other words, we reject the null hypothesis. So all of the science that we do occurs in this imaginary world where we always assume the null hypothesis is true or that nothing is going on. And the p-value represents the probability of data in this world. It tells us the probability of your result if we assume the null hypothesis is true. And so one way we might look at this is a mean difference, where one group comes from a different population than the other group. And we represent this with a mean difference. Uh, in other contexts, we might represent this with a correlation. So basically, this p-value is telling us, are these two means different from each other? And that's the way that we interpret it. But some downsides to that. A study that has a significantly large sample size, uh, in the thousands or in the tens of thousands, is always going to find a difference between means. Or in other words, you can get a statistically significant result by chance, um, where you have a false positive. Your statistics tell you that your means are different, but in reality, there's no meaningful difference there. You can also get non-significant results by chance. This is a false negative, where your statistical test tells you, no, there's no difference going on, but there is a difference in reality. between the means. So just because you have null effects or a p-value above 0.05, that doesn't actually mean that there's no difference at all. Instead, there could be a difference, but you lack the sensitivity in your statistical analysis to find it. So here, let's say that our p-value is 0.07. So do we just throw these data away and say, nope, they're not statistically significant? No, we might not. Instead, we have to think of another way to quantify this mean difference other than a probability value. So what do we do? Now remember, statistics can be generalized. So values like p-values are all really tenuous, or in other words, they are dependent on a lot of different things like sample size. So instead, we can use effect sizes to generalize to the population. One effect size that I'm going to show you today tells us how far apart two means are in a way that is psychologically meaningful or psychologically pleasing. And you may have calculated this before. The statistic is called Cohen's d. And in the numerator, oops, sorry, we're, yeah, in the numerator, we have the difference between two means, and that's in units of the scale. And then we take a standard deviation of the two samples. So it's a pooled standard deviation or an average standard deviation and divide by that. What this does is it takes our mean difference and it puts it in units of standard deviations. Or in other words, it tells you how far apart the means are in standard deviation units. Um, so we can use this in all sorts of statistical tests. And you're going to learn one called Kramer's V in an analysis called chi-square. When we talk about ANOVA, we're going to use eta square. In this class, we won't be talking about regression, so you can just ignore that. So I've got a calculator available for you on D2L that can help you to calculate effect sizes. So let's say this researcher had 10 individuals in a Stroop task who were doing a hard Stroop task. And he measured how long they took in seconds to finish the task. So let's say they took 42 seconds. Okay. And I'm going to pull up this calculator that is available for you on D2L. And I'm going to make sure that I'm sharing the correct screen. Okay. So here you can just start to plug in this information. We have 10 individuals who took the Stroop task, and it took them 42 seconds with a standard deviation of 10. Okay. And we compared them to people who were in the no interference task and how quickly they did it. They did it in 22 seconds, and they also had a standard deviation of 10. So here we found that these two means are two standard deviations apart. That's a really big effect. Okay. So you can find this calculator on that should say D2L, not CC. That's a different website. D2L. You can find this on D2L. So here we would have had a large effect size. And we would report it here like so. Okay, so our D is lowercase and it's italicized, and we found a value equal to 2 in our calculator. All right. So let's do one more practice problem here. And we're actually going to compare the results of two studies to each other. So let's say that we have a study that has Amazon workers, uh, and they're receiving some kind of sensitivity training on the IAT. And this is a really big study. In one group, we have 5,000 people who receive the sensitivity training. And let's say that their mean on this task is 0.45. Whereas the folks who were in, oh, I'm sorry, that's a standard deviation of 0.20. Okay, I'm pulling this information from right here. And we found that they showed less racial bias than the other 5,000 people who did not receive the training. Okay, so their bias is lower. These are their bias scores. And they had a standard deviation of 0.17. So this is a pretty sizable effect. But look at this t-value. This t-value is very large. It's negative 27. I've never seen a t-value that big in a study. Um, so I wonder if this effect is psychologically meaningful. Or in other words, should we do this? Should we do this thing? Should we be giving people this sensitivity training? Let's compare it to another study in which they did something called behavioral mimicry. This is where you mimic a person who is doing a task, and it's said to actually reduce biases toward folks. So here we've got a mean of 0.22, standard deviation of 0.20, and there's 20 participants in that group. Whereas in the other group, we've got 0.55. Our standard deviation is 0.23. I'm pulling this information from here. And our sample size is 20. Now, even though this t-value is way smaller than this one, this effect size is much bigger. Or in other words, we're going to be more likely wanting to use this behavioral mimicry technique for reducing bias than using this sensitivity training that the Amazon workers are using. Now, don't make any inferences from any of this. I'm just making this up as I go. This is not really a real example. These data are made up. But what this shows you is that t-values, whoops, and p-values are not necessarily reliable indicators of the strength of a manipulation. Instead, Cohen's d is a much more reliable indicator of that strength. So you're welcome to use this calculator in your class. There's really no assignments associated with it, but I wanted to just show you that it's a really useful tool to be able to identify which studies have stronger effects. Okay, so that wraps up lecture for this day.